I'll now hand it over to Dr. Khare, who will talk about networks and computing. Rohit.
Great, thanks. So, good afternoon. The point of this exercise today is to go over some of the basic fundamentals, things about computing and networks that are true and going to remain true for as far as the foreseeable future goes. We're not going to get too wrapped up around what startup A does, what startup B does, what can be done with this new kind of hard drive. And so in each case, if you feel jargon or if you feel there's a theorem, something you can refer back to in the text or the glossary, please feel free to interrupt. One major change is we're going to give this a little bit more time. So with that, the agenda. The problem is that we do live in an information-based society. We're all a little overly familiar with computers. They're all oversold to us all the time. We have the frustrations of working with them. And we, as information workers, can stay at this level above where we think we know what's going on. And that's where we want to take the covers back from off of that. And so the thing to keep in mind is also how this track relates to and differs from the other tracks. You know, AI and robotics is a lot of fun stuff that you can do when you have computers. Bioinformatics is a lot of very important implications when you have lots of compute power at your disposal. It's something that amplifies the pace of working with everything else. So in the first 2 hours, that's before the break, and we'll take a break inside as well, don't worry. I'm going to go over chapter 2.1 in the notebook, the core concepts. And then we'll go a bit into the speculation part about where we think some breakthroughs might lie. In the second half in the afternoon, assuming we've kind of stayed on schedule, we'd like to drill into some of the more thought-provoking parts of what happens when we have computing and connectivity embedded into almost any manufactured device you can think of. And that's going to have implications in society, legal, privacy, regulation, ethical implications, as well as industrial implications in almost every sector of the economy. And with that, one of the major things going on right now that helps set the stage for this revolution is, of course, social networking, obviously a very current buzzword, Facebook, LinkedIn, all of that. But it presages a much more important thing about how the internet and networking are not just affecting our technology, but they're affecting our culture. And for that, I am going to defer to Salim Ismail to take us on a bit of a step back and a tour on how this idea of the social internet, how we're connecting people to form ad hoc groups, how we're able to even bring together a group like today's SU program in a way that wasn't possible in the social structures of just a decade ago. So what's important to begin with now, so we dive in, is this classic chart from Kurzweil's work on understanding that computing is not a breakthrough since the Apple II was invented, or since the Khare was invented, or even since the first computers were invented after World War II. It's something you can trace all the way back centuries. And in fact, one of the great early pieces of work of Kurzweil's was getting the attention of a lot of us that you could actually trace Moore's law, not through just the era of ICs, but all the way back to the eras when we had mechanical computers and to the days when we just had calculators. So the core concepts we're going to handle here, there are 10 of them, just because we're not all binary people. We seem to like things in 5s and 10s. But they helped us organize our thinking a bit. And the first half are about the fundamental limits of mathematics, the properties of computing, the ways networks connect people. And then the second half of the core concepts are going to be about the ways in which the computers help us in the real world. All these things we do with UIs, with printers, with plotters, with video conferencing, social networking, and so on. And finally, just again, that reminder that at any point, if someone has a question with some of the things we've looked at this morning from AI and robotics, this question of where the dividing line lies and where the promise lies, we hope that by the end of this class, we'll be able to have a discussion and see if there's some understanding about those boundaries. So this begins with an old joke. There's one idea that I've found helpful at a higher level in tying together these 10 ideas. And it begins something fairly abstract, the idea of indirection. The problem with computers is you can only work on what you have right in front of you right now. And you'd like to sometimes say, wait a second, I don't have the answer right now. I need to go to a hard drive, and I'll get you the data, and I'll come back in a second once I have that. Or I don't have the answer right now. I need to go and check with the New York Stock Exchange, find out what the price of the stock is, bring it back, and then we can plot the chart. Or I don't know the answer. I need to go check with my broker, because they're going to tell me what price I can get on the dollar-yen rate right now. I don't know. And in each of these cases, we're replacing something that we know right now with something that we give you a promise or a pointer or an indirection. There's all these pieces of jargon. And we'll be talking about how we use layers. So the first piece of jargon is that indirection occurs across layers. We start with something very simple, like the ability to read the state of a light switch and say that's on or off. And then we add another layer saying, well, let's have addressing. So I've got a bunch of switches. Which one am I asking about? So keep this in mind as we'll come across this principle again and again. This quote is from the first computer that really used indirection for virtual memory. Obviously, you've all heard about the building-sized computers, but the idea being that if you only have a very small amount of working memory, how can you make that look like it might be twice as much? Well, you tell it this is the first half, and the other half is somewhere else. And that's what they invented here, and that's where they realized how much trouble they got into back in the 50s, and this classic warning that you can always solve a problem where I'm running out of something right now by putting in a layer of abstraction, but it'll bite you later on. So the very first model is a wire. A wire is a direct connection. There is no question about what it's being indirected to. You know, you put two Dixie cups on a string, you can talk at one end, you can listen at the other. You can't do both at the same time, which is a huge issue in networking, but you have the beginning of a connection. If you put a third Dixie cup on that line, or if you use electronics, you put another microphone and a speaker, you still have a party line. One person speaks, everybody listens. You have no way of selecting, I only wanted to talk to Neil and not Celine. Obviously, we put a switch in. The switch is a connection. Either I'm connected to A or to B. A switch that you can control remotely by another signal. Like, if Neil is trying to talk to me, then it should detect that and switch to connecting me to Neil. And when it goes silent and Celine wants to talk, it should switch and go to talk to Celine. That's the beginning of a gate. A gate is a switch you can control using the state of another switch. We're beginning to build this abstraction up. And so this is what people talk about when you see all these logic diagrams of an AND circuit or an OR circuit. This is one of these classic building block chips that was manufactured by the hundreds of millions, and it just has 4 NAND gates. These are logic blocks. But whether you see them in the form of a chip or in a mechanical form, or if you're going to see them in a nanomechanical form later on in Merkel's section, it's the same idea of I need to control whether the current or signal flows through one path based on the state of another. You know, spintronics, same thing. And again, gates today, of course, are in the form of transistors. That's the era we're living in right now. And they've been falling at this incredible rate. This is, again, one of the key exponential drivers that Ray is talking about in creating the notion and defending the notion of a singularity. Now, a gate is a static thing. It says, if Neil wants to talk, connect the line to there. If I want to actually have a protocol, like if Neil talks for too long, stop, connect Salim instead, or if both of them try to talk at the same time, decide by alphabetical order who's going to win, these become instructions. And instructions, of course, start with something much simpler than that, like addition, subtraction, multiplication. And the very first devices that we had, dating back to the late 19th, even arguably late 17th centuries, were hardware purpose calculators. Single purpose, you enter a number on a set of dials, turn the crank. After a while, you'll see the gearing change, and you'll see an answer at the other end. Later, around, let's see, just before the 1900s, so that's 1790 or so, we had the Jacquard loom. This was the ability to have a weaving machine that was controlled by a punch card. Now, this is one of the very first punch cards. This is from a machine called the Babbage engine that was actually on display, a replica that was made down the highway here at Mountain View at the Computer History Museum. And you can see they're not in great shape, and there's not a lot of holes per piece of paper. But the very idea that you have this giant piece of machine, and it can do different things based on what you put in the one side of it, is that next layer of indirection. I don't say it only does subtraction. I can have it do subtraction, then an addition with this other number, and then print that out. Now, that's still not very fun to work with. We start going from basic machine operations, we call machine language, that say, add this, write this down in this location, come back, check it again, compare it to some other value. We go to programming. So these are instructions that control how other instructions are executed. And of course, programming languages, you've probably seen a whole alphabet soup of them over the years. But the big picture has been, at each stage in the last 50 years, we've been trying to get more done with human productivity than worrying about whether the machine is any faster. And so what each of these generations began with 50 years ago down to the present day with Java and C++ is ways to use the computer to translate a higher level language into something that's more efficient for the actual hardware to execute. And so this evolution is the same thing. We've had to write all these programs that write other programs for us. The fundamental limit here, the fundamental reason that we're also excited about this is in the 1930s, we already laid down the theoretical framework for the fact that one computer can emulate essentially all the other ones. This mathematical abstraction is what allows us to talk about using one programming language and saying, I can compile it on my Mac, and then I can have it compile it for the iPhone, and then have it run over there on a handheld that has less memory and maybe a smaller screen, because I can emulate one computer inside of another. Now, it doesn't always mean that you need a big computer to emulate a small one. Sometimes you can do it the other way around. In the 1980s, around 86, I believe, there was a famous quote from Seymour Cray, the guy who was one of the real pioneers of supercomputing, and of course the eponymous Cray supercomputer. And Apple, this little dinky personal computer company, had just bought a Cray. And he said, well, they use a Cray to design the next Apple II, because they're doing the heat flows and the power supplies and the circuit simulation, because they had a supercomputer that could emulate a little Apple II. But we use Apples to design the next Cray, because that's what they needed to explore and coordinate their research. But the idea that one computer can compute what any other computer can is one of these very fundamental foundations in what makes computer science, and all these fun application areas, the layers on top. And this device is just worth thinking about as an abstraction. It's basically, this is an early diagram of it from one of the early textbooks, but imagine a very long paper tape and a very, very simple circuit. It can basically look at the tape, decide whether I should move left or right, whether I should erase what's there or move on. It's not very important to talk about the exact mechanics of it, but to say, no matter how tiny your computing device is, whether it can only do 3 things like read, write, and add, it's capable of doing everything else we've ever done with computing. And as a result, we're able to crawl this curve. And the important thing to take about this curve is not that, yet again, we can buy more computers for more dollars. It's that at almost any point in history of our field of networks and computing, you can buy the future. In a lot of other disciplines we'll be talking about, there's a day where we didn't have the human genome sequenced, and there was the day after when we did. There's a day when you can't do it for $10,000, and you could. But the difference between the kind of computing and networking resources that are available to a national government and the kinds that are available to your kids in the form of a video game has been about a factor of 10 million over the last 20 to 30 years. So when we talk about a Pentium offering a certain amount of compute power at a certain year for a certain amount of price, a research lab can imagine where we'll be in 5 years by buying a much more powerful computer. This idea that you can time travel by spending money is one we'll come back to when we talk about the evolution of user interfaces. At the moment when we kind of first invented Windows and mice and pointers and so on, it's actually over 40 years old. And the idea that we don't realize that progress often happens very unevenly. It's in some places already, unlike some areas, because there's not any lab right now that has a working nanocomputer or a nanofab. But there is a lot of places right now where you can figure out how can we use a supercomputer made out of video game parts, which we'll see a little later on too. Third basic item, of course, is storage. Once you've got hardware and software, you need some place to put the results of this computation. Again, there's a lot of hype about individual technologies, magnetic, electro-optical, different wavelengths of lasers and Blu-ray, holographic storage, the ability to directly manipulate atoms on the surface of a nickel plate and write at one atom at a time. But the critical way that we think about it, well, we, if I may speak broadly, the critical way to think about storage is not how many bits, because we're very inured to how much we can fit cheaply. You know, in 2019, you'll be able to fit every movie ever made in Hollywood history on an iPod. Okay, so what? The question we ask is, how long will it take to get it? Because the processor down at the core needs to be able to read and write to that. And if I can do 1 billion steps during the time it takes the hard drive head to move this far over and actually read one frame of video, then I've actually still wasted a lot of time waiting around. So the jargon here is called a memory hierarchy. When you have a processor, you're going to have some memory scratch pad that's right there because it's in the circuit that you're doing the addition over. Registers, we call them. And then behind that, we have RAM. You can buy on any ordinary PC. Behind that might be slower kinds of RAM, like a flash drive. Behind that might be a hard drive of varying capacities, the laptop being a lot slower than a server hard drive. And then ultimately, we try to do things like write them to linear magnetic tapes and put them in a vault somewhere underground. The critical thing about looking at distance is that time can also be thought of as how far away something is. Admiral Grace Murray Hopper, one of the great pioneers of programming and one of the most famous women in computer science, used to illustrate this in her lectures by carrying around a 1-foot length of copper wire. And 1 nanosecond, which at that time was an unbelievably small amount of time because we were looking at microseconds per operation, is 1 foot. Well, if 1 nanosecond is 1 foot, and your computer's running at 1 gigahertz, that means your wonderful 1 millisecond flash drive is miles away, maybe hundreds. In fact, at one point, there was a great metaphor done where he worked it out and said, you know what, there's computers today where your hard drives might as well be on Pluto. That was the argument for this aphorism that disks are becoming as slow today as tape was in the 60s. The important thing about exponentials here, the more fundamental point is, just because two technologies are growing at an exponential rate, because we've seen how computers are getting faster and cheaper, storage is getting faster and larger, but if one of those exponentials is even a slightly bit faster, it's going to completely swamp the growth. And that's what we live in right now, is that computers have been getting faster than storage has been getting faster and cheaper. And so people are really dusting off old algorithms that were forgotten about from the 60s because who has to do disk-to-disk or tape-to-tape sorting? So, and again, the usual issue about price and capacity and how we use that. Again, as I mentioned, you can use one computer to emulate another computer. You can use a small amount of memory to emulate a larger amount of memory. So let's leave that there. Magnetic storage, obviously, similar trend lines. This is another interesting one, which is the total number of bits shipped. So if an individual hard drive is a terabyte for $100 down at Fry's Electronics, that seems like a liberating thing. Because now I can back up all my PCs in the house onto it. I can keep all the movies we watch at home. Well, you need a couple terabytes for that. But as a society, we passed an inflection point a couple of years ago where we're actually producing more bits each year than we had last year. So the rate at increase of amount of disk storage is exceeding what we have as kind of almost an installed base. This means that actually it can be very cheap to store everything, but we might never find it again. And finding it sounds like a simple problem, but finding things and making sure what you get back is the correct copy. If there's 10 negative prints of Casablanca and all of the other ones are master copies and printed optically, if you find one in a library somewhere, you can decide it's probably the right movie. But if there are 1 million copies, each doctored, pirated, modified in some way, do you know what you pulled back actually is the thing that you're looking at anymore? So there's a consequence much larger than just worrying about, hey, it's cheap. So we're almost done with the first half of this. So the next piece of jargon you'll hear a lot is algorithms. Now instructions, of course, were the step-by-step, load this part of the matrix into register A, add it with that, multiply it by what's in register B, write it back out to memory. We have programming languages that make it a lot easier to just say A plus B equals and store that in C. But the algorithms, of course, are the instructions that we use to write down those instructions. If you want to sort a bunch of numbers, you're going to say, well, I don't know. I've got 100 numbers here. Let me just pick 2 that are next to each other and see which one is larger and swap positions if they're not. And if I do that for every pair, there'll be kind of a little bit of this jagged pattern. Then I might start again and come down and compare each of those pairs. And this is pretty much a very simple, dumb way to sort that will take quite a long time to complete, but it will complete. So that's a sorting algorithm that we're calling a bubble sort, where you just have the large value for this end is going to just bubble up step by step by step till it makes it to the head, and the one that's after it, and so forth. Now, a more clever algorithm for the same is quicksort, where you say, you know what, I'm going to take my list of numbers, divide it in half. I'm going to sort this half first. And then I'm going to take this half, which I know is all already ordered, and just join them up so that they're interleaved. Now, of course, how do I sort this half? You divide that in half again, and divide that in half again. And that's what we talk about it taking n log n time. The amount of time it takes is proportional not to how many items and how many times I'll have to compare it, but I only have to look, read, write, re-examine that amount of memory a lot less often. Now, the area of complexity theory about theoretical computer science and so on is these order bounds. And what's interesting about them is not that you can say, OK, if it takes me 1 second to sort 1,000 numbers, then it's going to take me, because of an order n squared algorithm, it'll take you 1,000,000 times longer to solve for only 100,000 numbers. It's that we can also prove that these formulas that tell us rules of thumb about how long an algorithm will take to execute, we can prove how upper and lower bounds on them. Mostly the lower bounds are what we care about. So we can talk about the fact that actually it's not whether I teach you to sort numbers using the bubble sort algorithm or the quick sort algorithm or the heap sort algorithm. It's that, in fact, you can say, we know that no matter what algorithm you have, you will not be able to do better than n log n, because that's the amount of essentially intellectual energy you have to put into that problem. You have to look at every number and know where they're going to go in the end. So this sort of result is the most profound thing that you should take away from it, because there's a lot of hype about how much cheaper and faster computers get. But there are problems that will not be solved in any reasonable amount of time, even with more compute power. There are things we can do with Google today when you have something that literally, to my mind, was unimaginable just 5 years ago. The notion that one private corporation can own several million computers and funded by advertising. But if you're trying to solve some basic problems like in parcel services, planning out tomorrow's delivery schedule. I need to pick up packages from all over the country, decide which flights to route from which cities to the next city pair. Once I got the packages in the city, decide which goes to which trucks, decide from which truck to go to which neighborhoods in which order. You actually have to test every possibility. Now, it clearly sounds like you could take any one proposal saying, all right, let's take these 400,000 packages and let's send them in this following routing order. They go into this plane, which goes from point A to point B. And in polynomial time, i.e. something proportional to n, we can decide, how long is that going to cost? Is that a good answer or a bad answer? But if you've got an exponential number of possible combinations of strategies to sort out, you're not going to ever catch up. Now, in practice, there are tons of actual results in algorithms. Clearly, UPS works today. Airlines work today. We satisfy, we approximate. We have lots of ways of getting around this fundamental limit. But there are problems that are so complex that we don't know how to solve them in polynomial time. And this article that I'm holding up here is actually last month's Communications of the ACM, which is one of the primary scholarly publications in our field. And what's funny is this cover story was just kind of desultory, kind of checking in on the progress of this famous problem that has eluded us for decades now. And really, it's not getting tackled anytime soon, because frankly, the prize is not realistically in solving these non-polynomial or NP problems quickly. The prize is going to come to the person who proves once and for all, no, we can't. But even there, people talk about this as going to be a huge project. But this article showed up 3 days later in the New York Times. And that was, I think, probably an interesting moment for us, because we were right around curriculum planning here by saying, what does it mean that an idea as abstract as that shows up in the business section of our Linus Daily newspaper? And it's because these problems that we thought of as fairly esoteric are happening more and more often in business today. We have so much data that we want to do things like figure out what's the optimal way to target advertising between East and West Coast, between genders and time slots and shows, and how to buy our ads. And these actually are that class of problem, these optimization problems. Now, algorithms also have fundamental limits regardless of how fast the computers are, based on how much interaction they require between if you try to split in multiple machines. Clearly, you see this every day in management. Simply adding more people to a team can make the whole team slower. It doesn't always make the job get done faster. And no matter how many people you add to an accounting department, if you're trying to do an audit, at the end of the phrase, everyone might have audited each department separately, but someone else has to sit there and review the figures and join them back in. That last step, the bottleneck, can eventually dominate the entire process. And so while we talk about these popular techniques, and we'll talk about this buzzword MapReduce in a second, another important name that we use in CS and software engineering is Amdahl's law, which reminds you that adding more computers ultimately can't make the serial part go away. And so if, in the end of the day, you can have a frame of a Pixar movie rendered with every couple of square inches of the screen done on a separate computer, but if you need to overall color correct the whole thing, you're going to need to take that process, might be the thing that takes the most time. So, oh yeah, this is the part where I pointed out that actually, not only is it a novelty nowadays that people build supercomputers out of a rack of Sony PlayStation 3s, apparently there's one, Chris tells me, in production at the Homeland Security Advanced Research Agency for decrypting passwords. You know, these things, computing goes one level to the next. This is MapReduce. This is just a slight aside into a buzzword you might have seen even in places like Business Week, saying, what is it that Google has figured out that all these other companies haven't? And one of the fundamental things is that Google knows and learned about 3 to 5 years earlier than the rest of us in the industry how to effectively program tens of thousands to hundreds of thousands of computers at once. This is just not a discipline you can really wrap your head around until you actually own that many computers, and very few of us did. Now, this example, you'll appreciate this one, is particularly bad because you have to separate the word map, as computer scientists use it, from the map that you see on screen, which is the actual map of Seattle here. But their idea is that if you got a query saying, I need to build a map right now to send down to this website, saying I have a picture of Lake Washington somewhere in one server, I've got a highway map, I've got live traffic feeds, and I've got the geographic place names, because if it's a French person looking at a US map, they might like to use the translated place names across the border. This problem is I need to do a search. So I'm looking for Lake Washington, I'm looking for the freeways, I'm looking for their traffic. You then say, that's going to be a whole bunch of rectangles that I need. So please go to the traffic server. I need this quadrant from this range to this range, and so forth. This goes out over the network, gets shuffled to the thousands of machines that each hold a piece of the map, the other couple of hundred machines that hold the live traffic data, and so on and so forth. Each of them simply answers by saying, OK, you've mapped this down to one tile that you need. Here's the tile. That gets sent back over the network to a bunch of machines and then reduce it, where reducing is taking all those tiles and forming the map that they send down to your web browser, which finally then looks like this. So this is a technique for just is really simply talking about, take a set of web pages, take every document, take every word in it, and then now say, all right, we have one machine over there, index all the occurrences of the word singularity, and then it has a word count. So this idea of how do you use multiple machines, MapReduce is one example of a parallelized algorithm, but it's still no panacea. We still can't solve a bunch of things well. Even at Google, the process of deciding PageRank, which sites are more important than others, these are jobs that still take hours, used to take weeks, even with as much compute power as they have. So telephones are frustrating because we used to be able to teach people with reference to phones. And those phones, rotary dial, copper wire out the back, electric microphone, they don't exist anymore. It's not as bad as finding the kids who show off, hey, look at my iPhone app. I can actually dial a number pad. What is that thing? But the critical distinction is the original phones, of course, used a single copper wire, hence the party line, hence the stringing up of a line dedicated from the factory site back to the owner's house in downtown. Hence the operator, the switchboard operator, literally what we talked about earlier, having a person say, on the party line, I need to call Neil, and then they're deciding, OK, hang on, and then actually taking a patch cord and connecting the wire that came out of my house to the wire that's going to his house. And it's a pretty amazing idea that the entire phone network for a country is actually just one gigantic machine, whether it's electromechanical relays or now transistors, but the idea that you could actually trace a single connection from point A all the way to point B at that moment in time. So in this model, we're called circuit switching. What we want to do is, of course, not waste all the wire of stringing up a pair between every possible house and every possible connection. We do use these switches. And hence, of course, telephone numbers that direct those calls when we eventually invented direct dialing. But circuit switching was, I need to create, set up an entire pathway. Then while those people are talking, I'm going to bill them for it. And when they're done, I tear it down. That's why, of course, no one can talk at the same time. You have all circuits busy. You have all these kinds of warnings. But that fundamental model ran what we knew about for computing and networking for an almost uninterrupted 50 years or so. Now, the reason that became an interesting area and drove all this research was if you have a copper pair between point A and point B, and it's 3,000 miles long, and it's going through all these gateways and power amplifiers and reducers and maybe even being transcoded to microwave and sent over the mountaintop and then put back at copper at the other end, you have this abstraction of you're going to lose bits along the way. You can not just lose bits because there was noise on the line or an electrical static, but bits can flip. So what you thought was a 1 could become a 0. And we talk here about then coding systems. Even back before telephones to telegraphs, we had the Morse code. The idea that the receiver and a sender are going to use this abstract channel that will take some amount of time to transmit a bit of information from point A to point B, but it might lose it or it might transform it. And whether that's now microwave or copper or acoustic or anything else, it really doesn't matter. This result from Claude Shannon, right after the war, was one thing that really revolutionized the field of information theory. The idea that there is a Shannon limit. It says for any channel with a given signaling capacity and a given level of error, no matter how clever you are, you will not be able to transmit data faster than the formula says. And that's because people would come up with systems like, hey, well, what if we repeat each bit twice? And then we know that one of them will be the right one. And you'll say, well, no. Because if you got once it said 1 and the second time it said 0, you don't know whether to agree or disagree. Say, great, we'll send it 3 times. Best of 3 wins. Well, great, but now you're using only a tiny fraction of your capacity, and you're using only a third of your capacity. And so this war began in terms of coding systems, right? Cryptography, decryption, channel coding, turbo coders that are in your cell phone today, they're all part of one continuous revolution in the field of information theory. But this model of a circuit and a coder really makes sense only if 2 people want to talk continuously over a certain period of time. Now, if you're going to log into a remote computer, as was getting popular throughout the 1950s to the 1960s, because computers were expensive enough that you'd rather have one big one at the university and give all the faculty member cheap teletypewriters. They're going to type and say, log in, and they're going to wait, which, of course, to the computer might as well be an eternity until it gets another message saying, OK, now password. If you think from the economics that the telecom companies face, this is where packet switching began, saying, well, what if I could use the computer at the other end and send messages that are bound to many other computers at the same time? Essentially, fill in all those gaps in between keystrokes with other messages. And theoretical concept breakthrough was 68, 69. By 1970, you had some federal money coming into this problem. And here I'd like to defer to a slide from Vince Cerf, another member of the faculty. I've had the pleasure of working with a lot of interesting folks over the years. But here's an actual 1999 vintage slide on the exact problem, which was, it's not just a new idea if you're a circuit switching telephone company type in 1969. It's a terrible idea. It throws away everything they ever really sweat and blood and tears for in terms of guaranteeing connection, guaranteeing a clean signal, of being able to say, this is the reliability of the Bell system. And so, hence again, the need for going around the system, federal funding, academic experiments. But in this context, for them to invent something like the ARPANET was a real breakthrough idea. And so if you're looking here now about around just the early 1980s, what you see here is a map, not of course of the whole country connected, but all of its interesting centers. The area around Cambridge, the area around Silicon Valley, the area around DC. It's on this sort of map that you could see not just the leased lines that were connecting directly to air bases, but these couple of microwave or satellite links going off to London and so on. But this idea that packet switching didn't just save us money in some sense because we could use all the gaps between everyone else's transmissions. It also made it possible to bridge different sorts of computer systems. Because the kind of computer and operating system used at Berkeley doesn't have to be anything like the ones being used over at Stanford. They just have to agree on a format for sending one packet of information, saying, please deliver this to machine so-and-so number. And the machine over at Stanford will say, great, I'll accept all the packets that begin with this prefix because I'm going to deliver them to any machine inside of Stanford. This internet then grew out of that pretty seamlessly. There's a lot of arcane arguments in the history of technology and what's the ARPANET and what's the internet. But by the point you hit this breakthrough, you begin seeing the academic use of the internet peak up. This is starting in 1990. And right here, this knee in the curve, that's when the NSF decided it wouldn't continue to be illegal to use the internet backbone for commercial purposes. And from this moment, you see this leap of, not just email over proprietary systems like MCI mail or AT&T mail, but the open worldwide global internet mail that we see today. And of course, the trend continues. The unit that we use, of course, of describing network theory and how we write software for it is something we keep talking about, the network stack. And once again, we'll talk about indirection here, which is that you'll say, oh, well, I'm going to have a competing standard for the kind of copper wiring that's good for 1 megabit Ethernet physical link. And they'll say, well, no, I actually have a chipset that can run 100 megabits over the same old wiring, and that becomes a different physical layer. But the problem, can I transmit a bit? Can I transmit a frame? Can I transmit a packet? Can I transmit entire emails? Inside that email, can I include a graphic annotation? It's going to be a GIF annotation. Can I encode what language is the email itself in? Is it going to be using the English character set or the US one or a Japanese one? And each of these layers of abstraction is how we tend to think. That's even how we organize the groups that work on these standards. So I'll say, I'm an application layer person, right? Of course, the reality is when you go to these standards meetings, you realize that all the real action is financial and political. Because every time there's a change in one of these standards, someone has something to lose and someone has something to gain. And that's why you might have seen the news headline just this past week that we've finally approved the use of non-English scripts in domain names. So instead of .com, you can actually spell something out in Korean at the top level. That process began back when I was an undergraduate. So I'll let you fill in how long ago that might have been, but the politics around that are pretty big. In fact, I'm going to switch out here for just a second and talk about the sixth major concept, which is namespaces. Networking in general talks about the need for connecting machine A to machine B. But we use the web to connect from person A to person B, and we type something in that we read off the side of a bus. And we need to worry about the namespace this comes from. I won't repeat this entire presentation, but when you look at something like http://singularityU.org/EP, the wiki. What's going on is the browser sees that as something in its address bar. You actually type in a web address. But actually, you chop off the first part, SingularityU, and that's a domain name. And so you pass that to the domain name system, which raises its own security and concerns. We just talked about that. But essentially, because SingularityU has written a check and has a federal incorporation number, and they've gone to an ISP, and they've gotten this specific IP address for their web server, the browser now knows which machine to go to. Now, when they go to that machine, are they trying to make a web connection, an email connection, a video connection? It's called a port. The technicalities is that the web runs on port 80. But basically, it'll say, the browser needs to send a message to this machine. It wants to use the HTTP protocol that runs on port 80. And then that's going to go out from your laptop to your ISP. Your ISP is going to say, well, where the hell is this machine? It's somewhere in California. I need to decide which of the 15 other networks I'm connected to forward it. Do I send it to the East Coast, West Coast, back to the UK and back? This is why you had phenomena like, up until very recently, the majority of traffic going between any two countries in the world actually went back to the United States, because the internet had enough excess capacity here, and most people wanted to pay for connectivity to the US. So traffic between countries in South America would actually come back to Miami most often. But each step of the way, you go to a MAC address, and I say, OK, which link is it, and phone numbers, and so on. Same thing on the other side. After the URL SingularityU, we have the wiki, and we look for the page that has the course notes today. That is another name. We pass that along to the web server. It says, OK, what is this file that I'm going to find the course syllabus in? OK, it says this is going to be the path name, so I map that to a disk file. Then I have to go say, OK, which disk, which controller, which sector, which bits, read them off, send them all the way back up. So the critical issue with the namespace is it's a form of agreement, a kind of constitution between the different systems that are going to play at this level. And the question you have to ask at each step is, who controls the decisions? So the idea that, when we look at the domain name, we can say which organization controls it, what protocol did every single computer that accepts the internet have to agree to, the basic host requirements, play by the game to figure out which one it's going to be. And that's how we establish all these temporary monopolies. it's a .gov domain, you can point to the exact US government official who is in charge of saying who it's going to go to and who it doesn't. And that's all these debates. So getting back to the main talk, and that's another constant. How many generations of PCs have we all owned? This, of course, is probably my 10th or 12th. And somehow they always cost between $2,000 and $3,000, and they're always slower than you want. That's an interesting constant. That's the kind of thing that motivates this section of the talk. Now that we're up at the level of websites. We're kind of gone, started down at Gates. We're up at a business like eBay. This is the Zen koan, or the single phrase I'd like to focus on here. eBay, which I'll assume most of us have used, is at one level a centralized website. There's one eBay. There's ebay.ca, there's eBay Motors, but there's essentially one ebay.com. But it uses distributed computing, a distributed database. The actual website with the information and the photos and the times and the deadlines and the logins is, of course, hundreds or if not thousands of machines in many time zones. But what that program is doing by running across the distributed database is implementing a decentralized market where anyone can, within reason, sign up on the network, offer to sell some gadget. Someone else can essentially, with a pretty unfettered freedom, decide to sign up and say, I want to buy that. But the format of a real-time auction with a deadline brings into sharp relief the exact questions at this next layer of coordination between computers. If I've got bids coming in, to pick again on our favorite examples, Neil at $1.40, and Salim, who at his time, at his laptop, at the same moment, offers $1.50, who's going to decide who wins? Is it a foot race because Neil's using a faster DSL connection and Salim is logged in over his cell phone and his bid is going to arrive first at my computers and I'm going to therefore give it to Neil? Or am I going to maybe look at the clock and say, actually, no, Salim's bid, his browser tells me he sent it just before Neil's did. But of course, if I did, then I have to ask the question of, why do I trust his clock? Right? If you try to do simple things, like anytime you try to break a tie because I need to coordinate which machine is correct, what is the correct price for a share of IBM stock right now? That answer isn't something you can, by law, set yourself. By regulation and law, you actually have to go to the New York Stock Exchange or another publicly listed exchange and get the best price you can for your customer. This means that your computer, when it displays the current price quote, is actually not saying this is the price. It's trying to say, this is my best estimate of what the price is over on that server over there somewhere on the East Coast. These problems are not merely philosophical distinctions of who's in charge here. At this point, Wall Street operates with flash trading with orders that can be opened for a millisecond or less. This is an abuse, frankly, in my opinion, and one that's recently been closed. But the degrees to which people will go to get an informational advantage over their competitors extends to an absurd rate. I've been to sales pitches where Intel is marketing its microprocessors based on the fact that they can process an order or a trade message coming over the internet in microseconds less than the next guy. I've talked to people who run the data centers where they have floor space in New Jersey for running the NYC main servers, and then you have another cage locked behind a padlock, which will be Barclays, another one for Lehman Brothers, another one for Bank of America. And they are actually selling circular layouts so that the speed of light delay between one bank and the exchange is not any worse. People were complaining like, I'm on the floor above and you're screwing me. This is serious business, right? There are people who write algorithms that are parsing what the Fed chairman says, and they don't wait to get to the end of the sentence before they issue a trade. They're trying to predict the sentiment analysis by the words coming in over the wire services. So coordination is the issue. And this is actually another area where there are some fundamental limits. So in the text, you'll find some references to some classic problems, the dining philosophers, the Byzantine generals. But if you come to one of these basic models, you've got three generals arranged around the side of the city. And if all three of them time their attack to tomorrow morning, they will defeat the city and take it over and win. If any two of them do, they will be routed. Now, the three armies are on three different mountaintops. How do they choose which morning to finally attack? They have to send a messenger, right? Let's assume they can't use flares. The Byzantine generals' problem originally dates back to saying if they are restricted to only sending messengers by horse who can be shot or desert, switch sides and lie, we're not even going to go there. We're just going to worry about the fact they could be messages lost or could take a very long time to arrive. In this setting, it is impossible to decide when to attack. And it's a little counterintuitive. Obviously, we attack cities whenever we want all the time. The coordination is solvable, but we take risks. In the abstract form, where you're trying to get a couple of computers to run the distributed simulation, like the NASDAQ model, if a machine can actually go offline for more than a few minutes or an arbitrary amount of time, you can't actually run these systems. So no matter what you do, you can't have a market that can survive in the following two properties. I'll explain a couple of these jargons. So mutual exclusion is the idea that if I'm going to look up the price of the stock or the current high bid on that item on eBay, there's only one machine out of the thousands that should have the right to update the price by a tick. Because if everyone does it on their own, you have this willy-nilly agreement problem. This is an area where there's a lot of math and a lot of algorithms over the years, but this is what Oracle is worth all its billions for, in short form. Fisher, Lynch, and Patterson are the ones who proved essentially that Byzantine general setting can't be solved. And more interesting than that, they established a precedent in the field that impossibility results are what win prizes. That, in fact, is very helpful to say this is what cannot be done with computers, even more so than simply arguing about I can do it 50% faster. And this was done in 1974. This was done just 3 years ago, was a derivative of that work, which is called the CAP theorem, which says if you are Amazon or eBay, you can either have an auction system where every single person logs in and sees that the current price and the high bid is this. Or you can have a system that survives when one of the machines, one of the data centers is hit by lightning. It's available. Is this some version of the website going to be up 24 hours a day, 7 days a week? Or you can have the ability that if Europe is served by a Europe server and the US has got a US data center and the transatlantic link is severed, shark attacks, pool halls, backhoes, there's a very long and very funny litany of ways that can happen. You can keep going. You can have any two of these three properties. No matter what you do, you're not going to be able to bet three. So Amazon chooses to be available and partitionable, but not consistent. Because in that worst case, when you have this run on Wii's like we did last Christmas, it is possible for Amazon to simply come back and say, sorry, your order is back ordered. We'll get you a Wii next week. eBay chooses to be consistent and partitionable, but not available. To this day, they schedule weekly maintenance of up to an hour on Saturday mornings in different time zones. Or, of course, the New York Stock Exchange, which is always available and always consistent, but runs in one data center. It's not supposed to survive partitions. So this intuition is worth coming back to eventually. And so when we talk about this current buzzword of cloud computing can save you money, but it can't get around these fundamental limits. Cryptography. So if you're going to do coordination, the next question is, how do I know it's Neil's bid, and how do I know it's Salim's bid? Of course, this is usually known in cryptography as names like Alice and Bob. And there might be a malicious intruder, Mallet. There might be an eavesdropper, of course, named Eve. And in the last 30 or 40 years of the literature in cryptography, Alice and Bob have evolved a very complicated life. There's a classic paper, after dinner speech delivered in the late 80s about the secret life of Alice and Bob, who clearly are adulterous lovers attempting to overthrow a government by conspiring against them, but have not yet agreed whether they have ever met before face to face. But in all these variations, can you play poker securely over the internet? These problems have been actually solved. This is one of the few areas where there's good news to report about fundamental limits. Because for a century, the problem was you could use a computer, a device, a special purpose machine like the Nazi Enigma, all the way back to the earliest ciphers, to take a message, transform it in a way that was secret. But the only persons who could decrypt it was anybody else with that secret. And that's a fatal flaw that's lived there in the whole time, which is that if you're going to require a secret in both people to be able to encode and decode, how do you distribute the keys? This, again, the so-called key distribution problem. And that can involve something as simple as diplomatic messenger pouches. It can involve bringing people back to the same place physically to write it down together and then agree not to ever say it on the phone, to things like when FDR and Churchill needed to have secure conversations in World War II, shipping essentially LPs of white noise by ship and by air so that if you had two exact copies of the same background noise playing simultaneously in London and Washington, and then mixing that with the actual conversation, they were actually able to communicate securely in what was known as perfect secrecy, because the completely random noise combined with the whatever speech you had equaled completely random noise. And that's one way to get perfect secrecy, but at the cost of an incredible nightmare of key management, because you have to actually send disks that are as long as any possible recording to every station, and you can never reuse them. So that's where we stood. Cryptography was something for national governments, but certainly not practical enough for electronic commerce and so on. And so, whereas I said earlier, in computing and networks, we do a lot of time travel by spending money. Here, you actually did have an overnight change in the world in '76, when in the public domain, Ravesh, Shamir, and Edelman published the first practical public key system based on Diffie-Hellman's work, with Diffie and Martin Hellman. But the idea was, I'm not going to use a single key for encryption and decryption. I can actually use two numbers. And every time I issue, I have a pair. And I have a private pair, and I keep it. And I can take the other half of that number and publish it publicly on the side of a bus, in the newspaper, anywhere you want in the world. And you have this asymmetry, where now anyone who wants to send me a secret message, as in Neil's browser connecting to eBay, can look at eBay's public key, encrypt a message, or the connection, this is the SSL or HTTPS lock you see, and know that even though this key is publicly known and I've encrypted it using this secret, the only party that can decrypt it is eBay. Vice versa, if we want to finally say at the end of the day, I received your bid, Neil, and you're the winner, and you don't have to fight with Salim over it, eBay can write that message down, encrypt it using its private key, and now anyone in the world can decrypt it and verify, yep, that was signed by eBay. And from this, again, come all these solutions for these previously intractable problems of how do you play poker without a cheating dealer and so forth. And so all of these things, all these great things followed from that breakthrough. It actually turns out that the British Secret Service and the NSA probably knew this between 3 to 5 years earlier. But that's actually only 3 to 5 years, not bad. I'll take a slight detour here finally in Section 8 on cryptography. In part because I just love this little algorithm, but in part because you're going to be meeting him later in the program. One of Ralph Merkel's many contributions to the field. Actually, one of Ralph Merkel's many contributions to many fields, which is what makes him an interesting guy, is one from the 80s called the Merkel hash tree. And it's worth imparting because it's an example of where mathematics and computing can create a trusted environment out of thin air. Almost everything we do in human society is based on authority. You know, the state has a monopoly on the use of violent force. The Federal Reserve has a monopoly on the printing of money. Banks have a monopoly on the ability to actually do a ledger that says who's got credit and debits and loans from the Bank of America. But if you look at these hierarchical structures, all of them have those same fatal flaws, that at any level of it, someone can be bribed, someone can be subverted, someone can be malicious. And so you look at the problem of notarization, the simple matter of saying, is this document signed at 11:59, or was it signed at 12:01 and no longer valid? And we have the system of notary public. So you supposedly go to a random person on the street who's a business person who you pay them exactly $5. You can't compete on price in the state of California or most other states. They then will sign it. They will witness you signing it. They'll put this paper seal that's supposedly really, really hard to forge. Yeah, right? But their signature then is on file with the county clerk. The county clerk has a file of those. The county clerk's signature is on with the Secretary of State. The Secretary of State is by the governor. The governor. The system of notary public is actually quite fragile, because when there's enough at stake, someone is willing to risk their notary license to forge that. So how would two people, mutually antagonistic, trying to negotiate a contract, both agree, yes, it's finally signed, this is the date it's in force? Because both of them could cheat. Suppose we have a crowd of 100 different people, all at the courthouse steps at noon, wanting to have something notarized, saying this happened at noon. What do you do without the court? So the rule is, take two people, any two people in the crowd. Look to the right of you, take that person. Take your contract, compute something called the one-way hash of it. Basically, take however many hundreds of pages of contract you have and give it a unique number as a formula over that text. That hash code will may only be maybe 25 characters out of the thousands of characters of the original document. You took the person right of you, you combine those two strings, and you hash it, and you get another 25-character code, or however long you want it to be, that now is uniquely tied because you and your neighbor are the only two people who know how to create that document. So you basically now sit back and you say, I've got my contract, I've got the number that I got from my neighbor, and I've got the number that resulted. Now, the two of you find the next pair, also still at the same noon on the courthouse steps, and the four of you do the same algorithm, where you say, we'll take your pair and our pair, join those, hash it, and we'll keep track of what the other guy said, the other pair said. And as you continue this pyramid up, what you have is one number that everyone's shouting out that you can go publish in a newspaper, and assuming that someone is not capable of forging every newspaper and every library in the country, you can take the contract, show it to a lawyer, show it to anyone else, say, here's the formula. You can replicate the number I had. You can say the number I had from my neighbor. You can see why we had this. You can replicate the number we had from our other pair. You can replicate that, the other 8, so on, up to the 16. And this number that's in the paper, for it to be forged, and for me to have lied about this, would require 50.1% of the other people to collude against me. So this is a great result. By tying everyone's fate together, the more people that hate each other that are in this crowd, the more trustworthy the system is overall. So these sorts of results are very fun, and that's one thing we base a lot of systems on. So in fact, for some years, a startup did run exactly this process. You can imagine that what you also do is you spread this over time. So their server would say, 5-minute window, whoever's got a document signed will notarize it for this 5 minutes. And then 10 minutes from now, you'll have a second 5-minute bucket. Then you take those two numbers, you hash them together, and you do it for the whole every 5 minutes for the week, every hour, every day. And in the Sunday New York Times, I haven't checked in the last year or so, you will actually find a classified ad with that number for the week. And that's how that system worked. Finally, at interfaces. So now we've built the computer, we've built the network, we've built the ways for them to run programs that talk to each other, we've built ways for them to securely identify who is at the other end of those computers, but we haven't figured out how computers actually work with people, how they affect the real world. There's a laundry list of possible technologies. And Chris and I will be glad to go through them interactively, but there's displays, audio, multimedia, things that were really big challenges throughout the 80s that are now taken for granted. Because some things, really, once they're solved, they're solved. I mean, video compression used to be an incredibly challenging thing, and now we expect our cell phones to stream high-definition movies. But the really difficult interface problems remain unsolved because they're involved in human behavior. If you're trying to do accounting, speaking of Intuit here, there's the breakthroughs where you realize for consumers, they don't want to do double-entry bookkeeping. So if that's what's going on behind the scenes, how do we create a cognitive task, an information interface, where they do just the task that matters to them, and the computer manages the background data structures required to do it. And so hence the original founding insight of Intuit, which was, what if we give the user a checkbook on screen and they write checks? That's what I'm familiar with. Let it do the bookkeeping so I can get reports at the end of the month about my assets and my liabilities. That's an example of interface problem. Yes, it's also an interface problem to decide what color will the check look like, and when I turn the next page, it'll make a little sound when it gets torn off or not, and that's all noise. But there are very real issues there. But what's important to think about is that it's how do we represent information? How do we interact with it? How is it that, the multi-touch interface that we have on the iPhone and all that, when was that pioneered? Well, the case study we talk about here is 2. The Dynabook was a project at Xerox PARC in the late 70s and early 80s, where Alan Kay wrote down a vision, was saying, someday every child will have a textbook where you have a screen on each page, and it's not just that it'll have books on it that you can read text, but it'll actually be able to program it and have animations and simulations, and things will play with it. Like, this is nuts. But they were able to build simulations of just that by using money to travel in time. And so the laptop computer format, arguably traces to this moment. And then what is referred to very much as the mother of all demos is this one by Doug Engelbart, who's still with us, in the Fall Joint Computer Conference in 1969 or so on. But what you have here is this tour de force of this guy who's been working off at SRI, Stanford, well, then Stanford Research Institute, kind of outside of the eye, a couple of grants, but the world of data processing and mainframe folks and computer science all get together. And what he shows off is this keyboard, yes, but this box that you move around on the table with these buttons out of it, made out of wood, And this other keyboard, which only has like keys, but you have to like press 2 of them at a time to make 1 keystroke. And then on screen, he's got these documents, and he's got his face because he's got live video next to a document. So he's talking about it, and somebody else he's talking to at the other end is editing the document with him. 1968, right? 1968. That's why it can be an exciting field to say that you can simulate the future. It can also be a depressing field because we know what we had 15 years ago. It's like, oh yeah, movies over the internet. We had that in college. Oh, sorry, now everybody has it. That's all you're talking about. So from this, collaborative work, right? The deep notions are not simply that NLS had these sexy gadgets and the mouse and documents, or that the Xerox Alto in '82 had Windows and WYSIWYG fonts. It's that it also pioneered the idea of collaboration. What if we have a single server where we keep the current draft of the paper, and anyone can check it out, edit it, and put it back? And the early IETF documents and internet reports were actually on this exact system. So the idea of collaboration, the wiki and the Wikipedia thing really traces back to this just as much. So sometimes an interface breakthrough can be how people cooperate. And Salim will be talking about that later in the afternoon. So we're going to close with this portion and, of course, lay the foundation. We're talking about quantum computing with Chris in a bit by talking about what are the fundamental limits of computing. This is something that Ralph will be talking more about during the nanosystems part of the course. But there's a couple of basic ideas about how much energy things take to communicate and how much energy things take to compute. And those form limits on the fact that, in some of the early designs they had for something as exotic as, if we freeze someone's body and 75 years from now, we attempt to revive it, and we need to repair all the damage done by the ice crystals. And we need to look at a robot that can go down in there and decide, aha, this is the cell wall, it's the same cell, I need to generate this protein, put like a Band-Aid across the 2 edges, and then as it warms up the body, it'll heal. Well, the computer, to decide what to do there, if built with the wrong kind of logic, could actually emit so much heat that it's going to melt the body anyway, right? So now we have all these problems. We're like, well, what if we put the big computer outside the body and it just wirelessly beamed the instructions back? But then you might say, well, wait a second. For me to transmit enough information for the computer on the outside of the body to know, here's where this protein is, here's this liquid part here, here's this next fat, globule of fat, well, you have to radiate information. How are you going to do that? You have to Morse code, ultrasonic, radio waves. You're just going to microwave the body and heat it back up. So these 2 ideas, that communications costs energy because you're trying to change the state at the far end. You're trying to signal a 0 or a 1. That's perhaps not so shocking. We have an intuition that to communicate takes energy, both to speak and from you guys to actually continue paying attention and listen and decipher what the person's saying. But computing takes energy. And computing takes energy for something that might be a little counterintuitive. It doesn't cost energy to add 2 numbers. It costs energy to erase one of them and put the sum back in that location. It's erasing information that takes energy. You can actually build physical computers using billiard balls, using gears, using mechanical rod logic, where essentially you have the steady state. If I have 2 plus 2, I can show this state of the machine over here. The arms will show 4. And if I have 3 plus 1, I'll still get the same thing, a 4 at the other end, but the 3 and the 1 are still in the system. And if I want to reset the system, I just push the rods back over here. It goes back to 0. Everything is here. We haven't actually needed to do much, like a pendulum swinging left to right. Doesn't net emit a lot of heat, just the friction from slowing it down. But if I want to take the 4 and now save space by overwriting it, that's where you are going to inevitably change the electronic state of a transistor, change the magnetic state, change the physical state of a nucleus of an atom on a metal surface, these ideas. And so there's only, these would seem to be a fundamental limit, how much energy computing takes and how much heat, therefore, it generates. There are 2 ways around it. One I just mentioned, which is mechanical reversible logic. If you actually don't bother erasing anything, you can actually run the computing in reverse and get your energy back. Kind of like, I guess, some modern hybrid. It's insane for a number of reasons that would become careful if you thought about it more regularly. Like if you were to send an email, would you really keep every single keystroke and every single frame of the team computer in the meantime while you're writing that email and keep it around permanently. I mean, it leads to a state space explosion. But within reason, for certain kinds of things like audio signal processing and so on, this actually has been a useful thing. Another way of getting around it is to not use clocks as much as we do. You know, when we use a gigahertz computer chip or a 4 gigahertz computer chip, you know, nowadays the things that Apple literally uses their supercomputing clusters to worry about is heat distribution and how to minimize the airflow through the computers to make them quiet. Well, that's because heat dissipation has become the dominating factor in CPU packaging. At its peak output, a modern server microprocessor has the same energy flux as a nuclear reactor core. Right? That's when you take a small amount of energy, but you divide it by a very small amount of space. Now, a large amount of that energy that's being burned up in your computer it's sitting there twiddling its thumbs, but that gigahertz clock signal is changing frantically every nanosecond, or nowadays, every 1/10 of a nanosecond. You know, a master clock and you subdivide it and all that. Well, that's essentially setting a bunch of information and then erasing it, and then setting it again and erasing it. And the actual dominant feature is how do we transmit a clock signal so that at one end of the CPU die and a 1/4 inch over here at the other end of the CPU die, everything is still in sync. You know, that becomes a dominant in power. It becomes a question of how wide your wires have to be on the chip so that the photons get there, or the electrons get there without impedance and not taking so long that now the computer on the other end is going to add A to B1 and you're still working on B2. Well, you can build a chip without that. Why bother with a clock? Right? If we build a human organization, I'd say, hey, come back, go look at that auction, look at all the bids, come back and tell me what the winning bid was, and I'll go write a check. That sort of task where you say, you go off, you compute it, come back to me, doesn't require a clock. It doesn't say, I will only listen to you if you come back here in exactly 3 nanoseconds. But you end up like saying simple things like, well, if I want to signal a single bit, you can't use one wire in asynchronous logic to say, I'm going to turn the signal on in half a second, keep it on for half a second, and then turn it off, Morse code. You actually end up using 2 wires, because you have to send one signal to say, this is now set to a 1 or a 0, and a second signal says, hey, listen to what I'm saying over there. So the mechanics of it are not the absolutely most essential. But this fundamental transformation towards saying, what if we laid out circuits so they didn't need to have clocks to always keep synchronizing this instruction, then that instruction, then the next one? You can actually go below that energy boundary again. And it was considered to be an insanely complex and ridiculous academic exercise. Again, when I was an undergraduate, they had just built the very first asynchronous microprocessor. Philips put it in a pager, and the battery life of the pager was insanely long. And that was the high watermark for the field for, almost a decade. No one went back to it, because it took a team of graduate students and PhDs to design such a circuit. But right now, as of this quarter, one of the grad students in that group went off to Cornell and had a student and founded a company and CTO and came to Silicon Valley and raised a lot of money, and we have Acronix. And Acronix builds asynchronous processors. And when Cisco or Juniper would go out there and say, we need to design our next router, we have a custom chip that can actually take an inbound fiber optic signal coming in that's been transmitted to electrical signals at 1 terabit. We need to signal it, process it, decide which packet goes where. These dedicated processors, they can't get Intel to build them a custom microprocessor for $3 billion. They use what are called field programmable gate arrays, or ASICs. So the application-specific integrated circuit is the idea that says, I can't build a whole new Intel-like microprocessor, but I can design a processor just for the task of routing secure network packets. And I design it, I lay it out, one of those NP complete circuit layout problems, and I ship it over to Taiwan. And by and large, Taiwan is it. There's about 1 remaining fab in this country that can do it. But Taiwan Semiconductor Manufacturing Corporation will FedEx you back a packet of your chips. And then you will test them and find you got it wrong. They will break. They'll radiate information. You'll refine your design and send it back to Taiwan again. That cycle is where routing lives today. Your only other option was another quick hack called the FPGA, the Field Programmable Gate Array. And imagine it basically as a blank slate. An FPGA is kind of like a memory chip and kind of like a processor. So basically, you can download onto it. I would like circuit A to do this and that gate to do that. You basically download the wiring diagram, run it for a while, then you can send another signal and erase it and set the computer up to do something else. Now, this is a brilliant idea. It ships you a lot of strips for Taiwan. But it can only run today, even now, things like maybe 100 megahertz. Obviously, things that we would recognize even colloquially as too slow to do something like a gigabit network processing job. So you'll see FPGAs and, oven controllers, prototype electronics. You'll see it be used to simulate things. But when it comes to building a real computer or a real electronic device, you have to go build an ASIC to make your camcorder work. Well, Acronics is an example of a specific product, speaking of Silicon Valley hype, where they take the ordinary designs that you would normally download to an industry standard FPGA, and they actually download it to a special custom-built asynchronous microprocessor that simulates an FPGA, and they're delivering 3 gigahertz now. And this is one of those paradigm changes that says, oh, I can get the processing power of an Intel microprocessor, but I can download it and update it within seconds and change it to a processor that works better for graphics, or a processor that works better for text analysis, or a processor that works better for fluid dynamic simulations. Now, there are caveats. But the bottom line headline is there, that you can now take what used to be the best of both worlds, and they're announcing chips that can process 120 gigabit signals for a pittance that you can reprogram on the fly. Because they've taken the power of this very abstract idea of building asynchronous versions of processors and hiding it under a layer of abstraction that says, just treat this like an FPGA. So don't despair too much. Moore's law has been declared dead any number of times. There have always been the process of simply in society saying, we're going to have that deadline, and somehow things get built. One wishes there was a Moore's law of rocketry. There you don't. The physics is a lot less forgiving. But we've bridged several fundamental transitions into different kinds of physical regimes, but computing is always kept on that curve. You can rely on it hitting that curve, but don't assume that curve will save us. There will still be problems that are unsolvable. There will be things that require trust that may not be trustworthy. And from that, we get to the remainder of the curriculum here. So now we're about 90 minutes in. I think we should at least take a break. I would love to take some questions. Anything we've got here? A couple minutes before we get to the next section. I'm going to go ahead and set the stage that we're talking about. What are the kinds of things that we see coming up now in these areas over the next couple of years? The ultimate one of those, of course, being the possibility that we might get around difficulty of factoring, possibly even the NP complete boundary if we have a new kind of computing device. And quantum computing is sufficiently weird and sufficiently new, even to me, that I'm looking forward to having a separate talk on the topic. So there's this section that you'll see in every one of the tracks in your program about projected breakthroughs in field X. And I mentioned earlier my belief about in computing and networks, we less often see a day zero, that before this point something was possible, and after this point something became possible for the first time. What we have are these trends. And I wanted to talk about the fact that, to me anyway, a breakthrough is not as often a purely scientific insight. A breakthrough, like public key encryption even, becomes a major piece of impact on the world when it leads almost 20 years later to the invention of electronic commerce. Right? This process of technological diffusion of innovation is an area of great personal interest. That phrase, in turn, is a piece of jargon for a book that perhaps should be on the curriculum, and I realize is not in your notebooks as a recommended reading. But William Rogers, in '64, wrote a pioneering text called On the Diffusion of Innovation, in which he was doing things like studying how farmers adopted different kinds of seed stock in the Green Revolution. And what we found in different communities as these innovations were brought by field agriculturalists and then picked up by major farmers or by small landholders and then went to the next village over, that these patterns recurred in the adoption of new kinds of circuits, in the adoptions of new kinds of video games, and that's been his empire of academic research and publishing and for years since. And it comes down to a couple of factors. How complex is something in terms of being able to explain what's going on to the potential customer? Trialable. Is it possible for me to just reallocate a part of my plot to the new seed and then compare the results? Dependence on how complicated is it to pass this innovation to the next person over. And so there's a 5-factor framework for how innovations diffuse into society and then become the actual green revolution, the actual revolution in incomes. And so again, there's a quick example about in the text about a jet engine. Is it the jet engine that's the revolution, or is it the economy mass travel airline that it enabled? Almost again 20 years after Frank Whipple's first jet engine prototype. In the area of IT, very specifically, I often try to get people's attention by saying, the iPod is a breakthrough because it rearranged the flow of a couple of $1 billion in a couple of industries. And yeah, Steve Jobs might be a genius for a CEO because he's done this in movies and in music and in computing and wireless phones. But these are not the kinds of scale of breakthrough I feel we should be thinking about. A breakthrough at the scale you might be thinking about is, how does an obscure programming language hack, also at that same Xerox laboratory we were talking about 35 years ago, become something that defines the look and feel of almost every artifact produced by our civilization today in the space of 35 years, which is PostScript. Right? PostScript, I imagine, I actually would like to do one of those few hand-raising exercises. Who in here even recognizes the term PostScript as this computer printing language? So about half, okay. Which is pretty profound for something that's pretty low level. It's like Intel inside, what difference does that really make? But PostScript was an abstraction layer yet again. It was saying, we have these laser printers coming out. And the laser printers need to have images drawn on the drum so they can be transferred to the paper and print out at high speed. Now, at the drum, we need to basically turn the laser on and off. So we have what's a raster, same pixels on your display today. And the raster image processors of the day were all proprietary and all different. So one of them would take a text string and then render it in this font, and then you'd say, make it black, and then move it over here by an inch. And the researchers at Xerox said, well, let's create a programming language not designed to manipulate numbers or to run spreadsheets, but a programming language designed to draw things on paper. And the PostScript programming language, in particular, had an arcane breakthrough in the notion of fonts in the way they were described. They didn't describe a font like Times Roman or Helvetica as a pattern of dots, but as a series of curves where you'd have to solve that equation and say, for this font, at this size, at this angle, at this piece of paper, on this virtual printer, these dots turn on and these dots turn off. Now, within that, there's a bunch more arcana. But the idea that a programming language would reshape an entire business to the degree that today they did, with very good reason, run an ad campaign that is unfortunately quite short-lived. But it was on our mind again at the last curriculum meeting because the founders of this company just won the National Medal of Technology a couple weeks ago from President Obama because they ran a campaign called Everywhere You Look. And if you see something printed on the side of a bus, a graphic on the side of an airplane, it's almost certainly at one point in its process rendered through PostScript. And that's a breakthrough. The fact that desktop publishing flowed from that, the fact that we expect things to look as neat and clean as they do, the fact that we can cheaply build printers and expect that if I'm a printer manufacturer with a new kind of color inkjet, I can directly sell to anyone who owns a computer today, those are all breakthroughs made possible by this adoption of this clever little programming language. So in that spirit, let's take a look into it. I mean, you can talk about the physics and the economics of why these things happen. Client-server computing, and now what we talk about as cloud computing today is a big trend. And it's taking advantage of the fact that we can make a couple of really big computers and then just use them more cheaply remotely than have a big one on everyone's desk. The laser printer was one of those exact examples of a departmental purchase. You couldn't afford back then to have a printer for every person. Back then it was $10,000, $40,000. It was by far the most powerful computer in the office because of how complex it was to render an image. And yet, of course, today we have $99 black and white printers at Fry's. So let's talk a bit about what can be done in each of these areas. These are basically points of discussion. I mean, augmented reality. Right here at NASA, they've had a lab that does research into flight dynamics and air traffic control. The air traffic controllers, classic problem of how do you coordinate inbound flights, use of the runway space on the ground, and runway incursions, which are probably the single leading source of threat to accidents in North American aviation today. And what they've been building over these years is a system that takes in all the abstract data about radar hits, positions, predicted times, flight schedules, and arrivals, and building various kinds of displays, head-mounted, projected on the walls, and so on, so that when you look out onto a runway at night, right at the edge where the plane will be, there is a glowing image of that airplane. This is a question of you're looking at reality and then you're augmenting it with something that's coming from the digital world. Now, again, a technique that was pretty state-of-the-art. That's a big advance. But for government procurement, which is a really big delay. So we haven't seen that really get as modern to production as it has. But that's slowly and steadily changing the idea of airspace management and ground handling management. At the same time, it's become a consumer toy. You can go buy an iPhone app now that when you look through it and looking at live video, and it recognizes buildings or QR codes. It'll pop up ads or current websites and logos of places. And there's one I saw just last week that uses the new iPhone's built-in compass and a hack that lets you track the location of other people on your social network. So that, just like on the old MASH army outpost, you can rotate it that way, and it'll say, 8,000 miles over there is one of your friends over in Korea, right? That's a crazy idea. But this idea of overlapping things. So augmented reality has been playing on all these underlying technologies. But in miniaturization of display, in better sensors, accelerometers, head trackers, there's breakthroughs in software engineering to take in real-time weather and so on. But it's a vision that animates an entire field. This issue of the Internet of Things, or this ubiquitous embedded intelligence. You can take a lot of cheap things, and if you treat them as a distributed sensor network, do some larger task. Almost 10 years ago, I remember being just jaw-droppingly amazed at the following concept that motivated this research team since then, which was ultra-wideband localizers, or crickets. And so you make these little cheap chips about the size of a quarter, and you can airdrop them over a battlefield. And they all have one sensor, which is there metal above me or not? And they have one radio on there, which is basically only powerful enough to reach the next coin over that might be randomly distributed. Can they form a mesh network wirelessly on the battlefield, ad hoc, wherever they fell down on the ground? Could they communicate with the same below the energy floor, ultra-wideband stuff that today, again, is happening, right? Today, they're aiming for a consumer product that you can go buy at Fry's, which would be wireless HD TV for your house. That's ultra-wideband we were talking about 10 years ago. If you think about a signal being like a sine wave, like you learned in classrooms, that's saying this is how we modulate a power or an FM radio signal. Imagine you only did this part, that one little arc. There's not even a complete waveform in it. So that's the kind of thing they're doing. Because you have so much compute power, you can try to reconstruct a signal from just that curve. That's an analogy of what's going on there. And they're talking about timing it within femtoseconds, so that now one of these coins or sensors can detect where that other one is to within a centimeter or two. But still, you got a cheap sensor, it's not very accurate, and it only covers about a square inch above it on the battlefield. The intelligence comes later, which is, can you transform a distributed network and realize, hey, wait a second, if enough of us in the same vicinity have all noticed some disturbance, then maybe what we need to do is correlate. So we'd be continuously checking with each other, saying, did you see anything recently? But not spend all of our time wasting our battery power talking to each other. And once we've all decided we've seen enough recently, can you actually get all of the coins on the battlefield to form a phased array antenna and send a satellite signal? Right? This kind of thinking is where you get these breakthroughs about taking cheap dirt ICs and reconfiguring them at will. Because if you had each of these antennas radiating at full power, they still wouldn't get a signal off of more than a few meters. But if every one of them knew each other's exact position, you can do the same thing we do with radio astronomy with the very large array out in the desert in New Mexico, which is you have a bunch of antennas or transmitters spaced out evenly, and they can form the virtual equivalent of a radio that is 10 miles wide or 26 miles wide or even 500 miles wide. And so this vision about saying distributed intelligence, Internet of Things. Yeah, right now, if you pick up a research report, Internet of Things will mean, what if Walmart has a radio chip in every single item they sell, and they could, just imagine what they could do. They could reduce wastage. They could avoid all the warehousing costs and shipping costs. They would know which stores were out of stock. And on one hand, the answer is, yes, that's true. You can go to a Prada store in New York right now and go pick up a bag and walk out the door, and they'll charge you for it, because they're using RFID. It's real. It's not science fiction. But at the other end of it, it's also completely false, because the amount of investment it takes to change your accounting, shipping, tracking systems to handle inventory so that the field that said, we have 1,000 pallets of toilet paper is capable of storing, no, we have 1,000 individual packages of toilet paper, each of which contains this, and each of which is priced that, and each of which is located somewhere over here. And sometimes the radio will be read, and we'll know that it was there, and sometimes the radio will fail. But then after it arrives, the next store will detect it again, and we'll be like, well, is it stolen? Did it reappear? It's a software nightmare. And so that vision of even 5 years ago has not come true. So it's not that sometimes the technology doesn't exist, but the synthesis that allows it to become a breakthrough doesn't exist. Mobile computing. Someone's pointed out that, look, it's about as reasonable as analog watch. Why do we're not going to go around and talking about the stationary computing market, but I think in a few years that might be just as insane to do so. But mobile computing, we're in the middle of it right now. What is the problem with it? It's expensive. It's uneven coverage. It's cell phone flakiness. It's The fact that none of us are really willing to use Google Apps in the cloud because the moment you go on an airplane, you're not sure if you'll be able to keep working or not. But those are things that'll take over time. And again, synthesis of a lot of different techniques. The answer may not be to fund the development of a satellite-based continuous, WiMAX, every person on the planet, every square inch will have 100 megabits of internet access. The answer might be, how do we use storage really cheaply and in ubiquitous places to simulate having mobility? We were recently shown a Zambian health card, smart card, little chip in it. And it doesn't just have your medical record in it. It actually has some of your neighbor's medical records in it. So there isn't actually a central server. It's whenever enough people come to the hospital, they just keep these fragments up to date, and they're able to reconstruct it. It's a Microsoft project they're doing as tech pilot out there. So those are ways of getting to mobility without necessarily getting hung up on the notion of, will one company provide satellite internet service over the entire planet? Google has been mentioned a couple times here today. Obviously, we're in Silicon Valley. We're all obsessed with them. But there's a good reason. They are actually running computer systems at a scale that no one's ever heard of before. And even if Microsoft and IBM aren't far behind, they also, as secretive and annoying as Google can be, are not as open as Google is. So this paper came out about 2-3 weeks ago. And it's from one of their chief architects and fellows talking about what happens when we want to manage tens of millions of computers within one corporation. I mean, as many computers as existed on the internet when we started inside of one company. So this is an example. This is a purpose-built data center facility in the Dalles, Oregon, which is built out there just like Microsoft's is built across the river a little bit further down because of cheap hydro. Cheap hydro, tax exemptions, and cheap land. That's God knows how many hundreds of thousands of machines in total, probably just under a couple 100,000, but only maybe a few dozen jobs because there's not many people you need to employ to do this if you have great software. This is what these guys specialize in. So they talk about the fact that this is one that is a quote from this talk about the joys of real hardware. And the idea that we try to worry about, hey, can we keep the electronic banking server up by saying, let's keep it up. Let's feed it clean power. Let's make sure if it has one hard drive, it has 3 if one of them fails. Let's make sure if it has a power supply failure, we put in 2 power supplies. And this is what you go to Sun or go to IBM and you buy a $30,000 computer server. That's because it has all of these levels of redundancy and protection built in. Now, if you want to go over to Stanford, you can go see in the window display in the CS department the prototypical Google server built out of Lego blocks, right? This is a completely different philosophy. They literally got a motherboard from Fry's and a couple of cheap disks and a fan and some Legos and built a case. To this day, you can go and find that they build their own motherboards. They Velcro parts in rather than wasting time on metal to hook them up. And what's the end result of all this? It's a very crappy computer, but it makes the economics of cloud computing entirely different than what we thought they would be. So yes, they'll overheat. They'll be gone for minutes. The power supplies will fail. The entire racks will go out. Backhoes will cut data lines between different centers. The number of insults the system can take is much more like a biological system than the perfect crystalline beauty of the old mainframe system used to be. They recently published a paper about the fact that RAM, at the scale that they use it, the memory chips fail at an astonishing rate. Well, astonishing to those of us who kind of assumed memory kind of worked. But when you have that many chips, even when you have extra bits of memory right there to do parity and checking and error correction, unrecoverable bit errors due to cosmic rays are now a significant factor at this scale. So it's a way of thinking about, the breakthrough is not that we can get cheap computers. The breakthrough is figuring out how to use them as a reliable one in concert. And then we've got, other specific visions. The idea of what are we going to do about information overload? A couple weeks ago at another workshop on the future of social networking at GigaOM, the next net, one of the speakers was saying, look, the problem with information overload from all the inbound email and RSS feeds and social network updates and tweets and SMSs is the cure for information overload may be more information, which is a terrifying thought. But his point was, look, we might need to know things like where you're located, where your friends are located, what your calendar is going to look like, so that we know, hey, this email you haven't responded to from Joe, you should do it to it now because he's coming by in half an hour for a meeting with your buddy and you might run into him in the hallway. Right? That kind of information refinery is a vision that's motivating a lot of new interesting work, both in academia and in startups today. The translating telephone, I don't know if you did discuss it in the AI track, but that vision is one that's a kind of a breakthrough. It's going to happen any day soon now, and the world will be a different place because of it. But it will be the result of decades of incremental work in other areas. But right now, you can pick up your Google Android phone and go to a web page and see a web page in Arabic and click the button and continue to browse the web in fractured, broken, crypted, but English nonetheless, because they're using all that statistical power to say, you know what, and this is Norvik's particular point, you know, we did talk about this one. Yeah. Great. But the idea, you know, when you pull it all together, the idea that you can open your phone, dial a number, keep talking, and have it be simultaneously translated, it's coming. But what will we do with it? I'd love to have a discussion about. And finally, quantum computing. So I see Chris back there, and that's what kind of sets the stage for one of the most extreme potential breakthroughs in computing, which is not just one that changes the economics of how much compute can you afford, and not one that changes the power distribution of can we miniaturize them sufficiently small enough, but changes the question of what is computable. So I'll take a break while we switch over to Chris. Thanks.